Welcome to section 3.1. Today we're going to learn how to find the determinant of a matrix, and this can be a rather mysterious process. However, we're going to start with what we know. We know how to find the determinant of a 2 by 2 matrix, and the notation is straight bars for determinant. So this is a number, and it's AD minus BC. We also know that A is invertible if and only if the determinant of A is not 0. And we're going to see that that result generalizes to 3 by 3 or bigger. We're also going to see how to find determinants of 3 by 3s and 4 by 4s in terms of determinants of 2 by 2s. So let's start with the cofactor. A cofactor is a number. And the ij cofactor of a matrix is the number found by taking the determinant of the matrix you get when you cross out the ith row and the jth column and multiplying by -1 to the I plus j. So that's a little bit confusing. So let's do an example where we're going to find 3 cofactors. Here's our matrix A. We're going to find C11, 21, and 31. C11. Using this formula above, it's -1 to the 1 plus 1, which is 2, times the determinant we get when we cross out the first row and the first column of A. And so that's -1 squared is 1. And then this determinant we know how to compute. This is AD minus BC, so this is just -1. C21, now we're going to have -1 cubed, which is -1, and our subdeterminant is 2001 because we cross out second row, first column. And so this gives us -2. Okay, pause it and see if you can find C31. Okay, hopefully you came up with 4. This is -1 to the 4th. And then our subdeterminant, we cross out row 3, column 1, and we get 2, 0, -1, 2. And so that's 4. Okay, so one thing to note is that these -1 to the I plus j, as I went down the column, they went from plus to minus to plus. And if I had a 4 by 4, it would have gone plus, minus, plus, minus. And across any row, it's going to also alternate sign, plus, minus, plus, minus. So just keep that in mind. And here's the formula for computing determinants with cofactor expansion. You're going to take the cofactors, multiply by the corresponding entry of A, and then take the sum across any row or any column. Don't memorize these formulas because it's going to be very hard to memorize the formula, but instead you're going to memorize the process. Kind of like finding, if you took Math 2A, third semester calculus, you knew how to find the cross product of 2 vectors, but you didn't really memorize the formula. All right, so let's use these formulas to find some determinants. And you can find the determinant of a matrix by going across any row or down any column, and you'll still get the same number. So in this first example, I'm going to find the determinant of A 2 ways. First, I'm going to go across the second row, and then I'm going to go down the third column, and we'll see that we get the same number. So to start, we're going to go across this row. So the formula I'm using is this, and then this first step, this is mental. You're not actually going to write down this step. After you get used to finding a couple determinants, you're not going to do this. So you take 3, and then you multiply by -1 to the 2 plus 1, because you're in the 2, 1 spot, and then you cross out the row and the column that 3 live in. So you cross out this row, this column, and you end up with the subdeterminant. So this is -3 times, and their subdeterminant is 2001. All right, and then we move on. Let me erase this because I'm making a mess. We move on. -1 times -1 to the 4th, that's a positive. So now we'll have minus, and our subdeterminant is we cross out the row and the column that -1 happened to live in. and we get left with 1, 0, 2, 1. Okay, and then we're going to get a minus 2, because negative 1 to the 5th is a negative, and then our subdeterminant is 1, 2, 2, 0. Because we cross out the row and the column that 2 live in. So this is if I were doing this problem on my own, I would start here with this step. I might write down the negative 1 cubed, negative 1 to the 4th, negative 1 to the 5th, but I wouldn't write down a 3 by 3 and literally cross out the row and the column. Too much work. I would start with this. I would do that step mentally and do that. Okay, so now what's this? This is going to be negative 3, and these are all 2 by 2, so we can compute the determinant by going AD minus BC. So this one is 2, and then minus 1, and then minus 2 times 0 minus 4 is negative 4. So I get negative 6 minus 1 plus 8, so I get 1 as my determinant. Okay, now let's go, same determinant, but now we're going to go down the third column. All right, so I've started this out. We're going to go 0 times negative 1 to the, this is in the 1, 3 spot, so that would be 4. And then the subdeterminant, I cross out the row and the column that 0 live in, and I get 3, negative 1, 2, 0. And then I'll get plus 2 times negative 1 to the 5th. So my minus signs are going to go plus, minus, plus. And my subdeterminant is 1, 2, 2, 0. And then finally, 1 times negative 1 to the 6th. And my subdeterminant is 1, 2, 3, negative 1. Okay, now this is just a big old 0. So in reality, I wouldn't have written all this down because I'm going to be multiplying by 0. So I would have just left it 0. So this is minus 2 times negative 4. And then plus 1 times negative 1 minus 6 is negative 7. So we get 8 minus 7, which is 1, same number. So when you're doing these problems on your own, if you're allowed to go down any row, across any row or down any column, you're going to pick the row or column with the most zeros in it, because that's going to require the least amount of calculation. So pause the video and try this one. Do cofactor expansion down the first column. Okay, let's see. Hopefully you got, let's see, I did it and I got 4. So this is going to be, if we're going down the first column, negative 2 times negative 1 squared times 0,320. And then plus 4 times negative 1 cubed. And our subdeterminant is 1, negative 1, 2, 0. And then plus 0. So I'm not even going to compute that subdeterminant. So this is negative 2 times 0 minus 6, negative 6. And then minus 4 times 0 minus a negative 2 would be positive 2. So we get 12 minus 8, which is 4. Okay. So now do this again going across the top row. Let's switch this to third row. Make it a little bit easier. This is going to, because look at the third row. There's only going to be one non-zero subdeterminant. So our determinant is going to be this is equal, and I'm using equal because this is literally equal, 2 times negative 1 to the 3 plus 2 is 5. And then my subdeterminant is, cross out that row, that column, negative 2, negative 1, 4, 3. Okay, so that's negative 2 times negative 6 plus 4, because it's minus negative. Negative 6 plus 4 is negative 2, so I get 4. Okay, and then the mysterious minus from Math 2A. So if you didn't take third semester calc, you can just ignore this. But for those of you that did, you'll remember that when we found the cross product of two vectors, the answer was a vector, and the second entry was always negative. We put a minus sign in front of whatever the second entry was. And I said, well, I'll explain that when you take linear algebra. Well, here we are. To find the cross product of two vectors, we put the vectors I, j, k on the top row, and then u goes in the second row, v goes in the third row. Now, if I use cofactor expansion along the first row, that explains where that minus is coming from in the second entry, because we get negative 1 squared, so that's a positive, and then the second entry is always going to be negative 1 cubed, which is a minus, and the third entry is positive. And then we computed subdeterminants, and so in this case, we're going to get 2, I'm going to write this in as a vector, 2, 5, negative 4. If you compute these subdeterminants, that's what you'll get. But that's where the mysterious minus the second entry comes from. It comes from cofactor expansion, the plus minus plus pattern. Okay, couple more topics here. We're going to talk about shortcuts, and then we're going to talk about determinants and elementary matrices, and then we're going to talk about geometry. So triangular, up here. So one shortcut is for a 3x3 matrix, and it only for a 3x3 matrix. And I used to think, well, I still do think this is kind of a gimmick. But when determinants were discovered in the 1700s, they were discovered concurrently in Japan and Europe. And in Japan, 3x3 determinants were computed like this by Sakai. And this is a postage stamp bearing his work. You can kind of see the pattern that we're getting. So one thing I don't like about this shortcut is that there's no way to do it notationally. The second is it only works for 3x3. And the third thing I don't like is it's very easy to make a mistake because there's a lot of arithmetic. But students seem to love it, so I'm going to show it to you. I will never ask you to do this. I will never ask you to do this on a test. But I want you to just be aware that it's out there. So, okay, I'll stop talking now. Well, I'm going to keep talking, but I'll stop. I'll just do this example. You copy down you write down the matrix, and then you copy down the first two columns. So you repeat column 1 and column 2. Then you draw diagonals, 3 diagonals going up like this through the numbers, and you take the negative of those products. So the product of these numbers on the diagonal is negative 6. So I'm going to take negative of that, which is positive 6. Then I'm going to take a negative 0. And then this product is 20, so I'm going to take negative 20. Then you draw arrows going down, 3 arrows like this. And you take the product of those numbers, but you take the positive products. So up here, positive products, negative products. So our first product is 0. And our second product is 0. And then we get positive 16. Then, to get the determinant, you add up all those numbers. So 6 minus 20 plus 16, which is 2. Yeah, that's 4. So, wait a minute. 6 minus 20 plus 16, so that's 22 minus 20, yeah, 2. Okay, so that's the last you'll hear me talk about that. Triangular matrices, this is not a gimmick and it's incredibly useful. If you have a triangular matrix, either upper or lower, the determinant is the product of the entries on the main diagonal. So here's an example. By theorem 2, the determinant of this matrix is the product of those numbers. 2 times 3 times negative 2 times 2, which is negative 24. Let me show you why that works. It works from cofactor expansion. So suppose we have an upper triangular matrix. So this is the same matrix here. I'm going to do cofactor expansion down the first column. Why? Because every entry is 0 except the top one. And so the top entry lives in the 1, 1 spot. So I didn't write the negative 1 squared there because it's positive 1. I just wrote the 2. And then I take the submatrix, cross out the row and the column that 2 lives in, and take the determinant of that yellow submatrix. So that's what you see in this next determinant bars, Now I'll do it again. Cofactor expansion down the first column. Once again, I'm going to get all zeros except for the top entry. So 2 times 3, and now I'm down to a 2 by 2 matrix. I can just take the determinant by multiplying the diagonal entries because this entry is 0. And so what I end up with is the product of the diagonal entries. No surprise there, negative 24. So like I said, we'll use that repeatedly, but mainly in the next section when we learn properties of determinants. So getting to properties of determinants, I'm going to formalize these properties that we're going to see. So we're going to see some properties here on this page, and I'm going to formalize these in the next section, but this is just to give you a feel for why they work. So do you remember what elementary matrices are? I hope so. An elementary matrix is a matrix you get from the identity by performing one row operation. So if you perform a scaling operation, let's see what that does to the determinant. The determinant of this matrix is k, where k is the number I scaled a row by. Let's do the swapping. The determinant of this matrix is 0 minus 1, which is negative 1. Row replacement, the determinant is 1 minus 0, which is 1. Now that generalizes. If you take an elementary matrix that's a 3 by 3, the row replacement one will have determinant 1. The swapping will always have determinant negative 1. And scaling a row by k will always have determinant k. Now let's see what these row operations do to the determinant of a just pedestrian matrix A. So here I've got a generic matrix A, B, C, D. Notice its determinant is AD minus BC. I'm going to do some row operations on A, and I'm going to observe, I'm going to do that by writing B as an elementary matrix times A, and then I'm going to observe in each case the determinant of B is the determinant of E times the determinant of A. So this is just going to be a bunch of observations. And it's a good practice with elementary matrices. So row scaling. If I scale matrix A, the second row, by k, I computed the determinant of that matrix, and I got k times the determinant of A. You can go through that computation on your own. Now, let's write B as an elementary matrix times A, B, C, D. What would that elementary matrix be? Well, if I want to scale the second row of A by k, the elementary matrix I want to use is found by taking the identity and scaling the second row of the identity by k. So that's the elementary matrix I want to use. This is my E. That's A. Note, determinant of B is the determinant of E, which is k, times the determinant of A. Because the determinant of A is the determinant of A, AD minus BC, and the determinant of this guy is K. All right, let's do another one, row replacement. If I replace row 1 by k times row 2 plus row 1, the effect on the determinant is no effect. The determinant of the new matrix is the determinant of the old matrix. All right, well, let's write B as an elementary matrix times A. The elementary matrix I want to use, I take the identity and I replace row 1 with k row 2 plus row 1. So 1k, 0, 1. All right, and note the determinant of B is the determinant of E, which is 1, times the determinant of A. All right, finally, swapping. If I want to interchange 2 rows of A and take the determinant, I get negative the determinant of A. If I want to do that by multiplying by an elementary matrix, the elementary matrix will be 0, 1. This is the swapping matrix. 0, 1, 1, 0, and then A, B, C, D. And the determinant of B is negative 1 times the determinant of A, which is the determinant of E times the determinant of A. By the next class, we'll be able to show if you have any two matrices and you multiply them together, their determinants multiply also. Now, here's one that's slightly different. Suppose we don't want to multiply just a row of a matrix by k. We want to multiply the whole matrix by k, so all the rows. In this case, there's 2 rows. I can't do that. So first of all, what is the resulting determinant? Well, if you do this computation, you get k squared times the determinant of A. If you want to do that with elementary matrices, you can't do it with a single elementary matrix because each row has to be scaled separately. So in this case, we'd have to scale row 1, which would be k, 0, 0, 1. And then we'd have to scale row 2, 1, 0, 0, k, then multiply by A. So it would require 2 elementary matrices. And then each one of these, if I call this E1 and this E2, the determinant of B is the determinant of E1 times the determinant of E2, because those both have determinant K, and then multiply by the determinant of A. Now, in general, if you want to multiply a whole matrix by a number, then the determinant will depend on the size of the matrix. Because if A is like 3 by 3, then you're going to come out with a k cubed determinant of A. So if A is n by n, the general formula for scaling the whole matrix is this. And again, I'll reiterate that next time when we talk about properties of determinants. So I'll go through all of this more carefully next time and show you how it applies to actually finding determinants. This is more like a touchy-feely section. Okay, last topic, geometry. And here's the theorem. The area of a parallelogram spanned by the columns of a 2 by 2 matrix is the absolute value of the determinant of A. Now, this can get a little tricky because the notation for absolute value is straight bars. Well, that also happens to be the notation for determinant, right? And so sometimes instead of writing bar determinant, so this way I didn't write, notice I could have written area. I could have written area is the absolute value of the determinant of A, but that would be confusing because it would look like magnitude. It would look like double bars. So I wrote straight bars determinant A. You could also write absolute value of the determinant of A. You want to avoid like a bunch of double bars. So just pay attention to when you see this, you have to use context. It wouldn't make any sense to say this is the determinant of the determinant of A because the determinant of A is a number. So this is absolute value. Okay, so let's look at why this might be true. Here I've got a matrix A, and the columns I'm going to call U and V. So A, C, B, D. Now, it's not so clear to see what the area of the parallelogram spanned by these columns is unless perhaps C is 0. If C is 0, then U lies on the x-axis, and we can easily compute the area. The area of that parallelogram is going to be the base times height. That's the formula for the area of a parallelogram. Base times height. Now the base is the absolute value of A. Now I should say absolute value because I've drawn A and D to be positive, but your parallelogram could go like this, right? In which case A would be a negative number, but the area is still positive. So absolute value of A times the absolute value of D. That's not a B, it's a D. Again, I've drawn D to be positive in my picture, but D could be negative. Well, by properties of absolute value, that's the absolute value of AD. But hey, that's the absolute value of the determinant of A, because the determinant of A is AD because C is 0. Now suppose C is not 0. Well, we'll rotate the parallelogram so that C is 0. Okay, if C is not 0, we can multiply by a rotation matrix, and notice the determinant of the rotation matrix is 1. It's cosine squared theta minus negative is plus sine squared theta, which is 1. So we can rotate it so that one edge lies on the x-axis. That's not going to change the area of the parallelogram, right? So the area will still be the area, but we can compute the area by taking the determinant of RA. And in the next class, we'll see that's the determinant of R times the determinant of A. But as I just mentioned, the determinant of R is 1. So we end up with the determinant of A. So the area will be the absolute value of the determinant of A. Okay, so here are some practice problems for you. There's 3 problems. Let me just mention what I mean by be careful with your notation. For this first one, let's just start you out here. The area is going to be the absolute value of the determinant of the matrix with these columns. So it's going to be the absolute value. I'm just going to write ABS for absolute value, and then the determinant of 1, 2, 4, 3. So the absolute value of the determinant of that matrix. So you can go ahead and find that number. Another way to write this so that you avoid double bars, you could write it's the absolute value of the determinant of the matrix 1, 2, 4, 3. Okay, so now I'm writing determinant as DET, determinant of this matrix, then take the absolute value, or I can write absolute value of the determinant of that matrix. They mean the same thing, but I'm just avoiding double bars. This is the same thing as, this is what you want to avoid. This is bad. Absolute value of this determinant, 1, 2, 4, 3. I mean, you could do that, but it's a little bit awkward. Okay, and so go ahead and figure out that that's 5. And then here are 2 just simple determinants for you to find. This one, I want you to do cofactor expansion on the top row. And this one, you're going to start with cofactor expansion on row 3 because there are the most zeros there.